So we're going to record it in two separate ways. That's messed up, isn't it? 5, 4, 3, 2, 1. Whee! Okay. So hopefully this will work. I'm not sure what microphone this is recording on, or if it is even recording on microphone. But I figured I would do this example. That makes sense. I didn't do this example in class. So, and I also wanted to record the example, so I'm going to do a twofer. Then I don't have to like process the video. Does that sound good? Yeah. All right, cool. Awesome. All right, so we have this example where we have like an I-beam that's subjected to bending. And we want to figure out and estimate how long the thing's going to live. So estimate the life of a cantilevered beam. And you know what I need is a pencil. Son of a gun. So here's me. Each one. Yeah. Cool. Thank you. I break a lot of legs. All right. Great. And let's take a look at this. All right, so I already looked up this I-beam. There's this information down here. Let's see, we're going to get a little higher. And it's got a fully reversed 62,500 foot-pounds. Seems very specific. The beam is forged and has properties of cold-drawn 1050 steel. The welds can be approximated as 0.25-inch radius fillets. The operating temperature is 300 degrees Fahrenheit and 90% reliability is desired. Want to emphasize that doesn't mean it will reliably fail at this life that we predict, only that it will reliably live longer than we're saying. Was that right? No. Yeah, I think I had that right. So one of the first things I might do is look up my materials. Since I'm good thing. So cold drawn 1050 steel. And I look up in table 820 for that. And 1050, we're like right in here. So the ultimate strength, what are we doing? We are in US units, okay. So 1050, did I say cold drawn? Yeah. 580. So that's going to be a ultimate strength of 100. Because that's the KSSI is in the parentheses right there. Okay. Good. We'll write that down somewhere. I'm also going to turn that 62,500 is equal to, oh, I didn't write out the units. That's in foot pounds. We want inch pounds. So that becomes 750,000. That just seems like a really large number to write, so I put it in foot pounds. Okay, so I think I'm going to start out by getting the next thing is the stress concentration. So first off, this thing is a weird kind of looking thing, so we have to kind of make some decisions here. This is like an approximation decision that we have to make. It's this comes up a lot in engineering, right? Where our stress concentrations are based on the information we have available, right? So this is probably going to be one similar to this, maybe. One of the first things we note, though, is that we have a depth, a width of this that we can have of the I-beam, but it's right up against a wall. So one estimate, one approximation thing we'll make is that we'll say, well, this D is infinite. So big D over little d that we need for this is infinite. Well, we don't have a line for infinity, but we do have a line for 3. So 3 is equal to infinity today, right? It's the best that we have. And then we can look at R over D. Now here's also another approximation we'll have to make, and I'm not even sure if I remember which way it goes. Should we use the entire width, right? So here's the thing, right? So there's the, looking at it from the side. Should we use this as the little d? Or should we zoom in right in there and think of this as the plate right there, right? And I'm not sure which one I chose to do. Should we use this as little d, or should we use that as little d? Because this to me seems maybe, just off the cuff without without peeking, and it seems to me to be the way to go. That makes more sense, because remember that all the stress is local. Right. It doesn't really care about how big this thing is, and this is really only that big, sort of like right there in the center, because this is an I-beam. So right out here over to the sides, it really just thinks it's a plate against a wall. Right. And we are, it doesn't have, well, maybe it is welded like right there. They might actually have welded right there as well, right, as they went along the whole thing. So hopefully I use that. So we'll take a look at the information we have. We have the depth is 8, but we have a flange thickness of 0.462. This is the one that I think we should use. And lo and behold, that's the one I used. Woohoo! So our big D over little d is infinite. Our R over D, we could say, well, we're going to approximate the weld as if it's in 0.25 radius fillet. So 0.25, and we have this average thickness, right, of 0.426. And I say it's 0.587. That's pretty darn big. We take a look at our information here, and we don't go up that high. But you notice these kind of flatten out. So once again, this is the best, and we're just going to do the best we can with what we got, knowing that this is going to be 50% reliability all the way along. But that's not a reason to just start throwing numbers away. We're going to try to get pretty decent numbers, but just take them all with a grain of salt. So that looked to me, I think I said back when I looked at this before, I decided to go 1.45. I think I actually might want to go closer to 1.4, but I have 1.45 in there. Like here'd be 1.6. Here's 1.5, so 1.45, I guess. We're going to stick with it because that's the numbers I have. Okay. We could argue about it though. So my KT is approximately 1.45. Then I go and look up, because this is we're modifying our stress concentration with notch sensitivity, the new thing that we haven't we recently covered. The notch sensitivity, we do have equations for it, but it's a lot easier for us to use the graph. So we come into here, and we have 100 KSI. There, we get a graph for that. That's nice. And our fillet radius is 0.25. Once again, we are off the chart. But once again, this also kind of has a plateau to it. Right here. So this is figure 626. So it has a plateau to it. There's 100. So what we're going to do as an approximation, we're going to use 0.85. Here you can see there's 0.8 there. Here would be 0.9, so 0.85. We could, by the way, run through equations to find this, and so that might be another option that we have. The process for that is to find that square root A thing from this ultimate strength, and then to plug it into this Q equation right in there. But we're going to go ahead and say Q is approximately 0.85. So all kinds of approximations already. So our KF, our stress concentration for fatigue, is found by way of 1 plus Knox sensitivity times KT minus 1. So that's 1 plus 0.85, 1.45 minus 1. I don't know how many parentheses I just put in there. 1.383. Seems silly to even have that many decimal places, but we read it from our approximations, but we'll just stick it in there. So the stress that we're going to get from this, we're going to go MC over I. And that I, we can actually go M over Z. We have an opportunity to do that because they actually give us the section modulus, which is the same thing as Z. Right? That's the, some books call it, some places call it S, some people call it Z, some people call it other names and things. But that all that is combining the C and the I together. You get to skip a little step. So 750,000 divided by our 14.4. And we get 52.08 KSI. So our max is in tension and compression is going to be that KF times our nominal, or 1.383 times 52.08. And we get 72.01 KSI. Now we want to start going through our equation that goes SE equals KA, KB, KC, KD, KE. And some versions have KF, SE prime. KF, just remember that KF is not that KF. Right. Just going to hammer that home, just going to keep repeating it. And then maybe, but and then I publicly shame anyone who does use it. That's not a good way to be a teacher. You shouldn't publicly shame people. That's not great. But it could be amusing to everyone but the person being publicly shamed. That's not good, though. That's not empathy. You shouldn't do that. Put them in the stocks and throw rotten fruit at them. Exactly. So we started with SE prime. That's 0.5 ultimate strength. So I can do this math. 150. Look at that. And just to be obnoxious, I put the 2 decimal places. I put 4 suffix. Maybe I want to use. I used the 10th edition when I calculated these numbers. There is a difference, but first off, we have to decide the surface condition factor Ka, which is equal to A times the ultimate strength raised to the B. But recall that we need that A and that B from a figure or table and not from equations that we had before. So I said the beam is forged, and we have that as a choice, is forged. Right here. So we have as forged right here. And it says to use 54.9 raised to the negative 0.758. And what did I do? I used the old version, which had, right? So the A I should use, but I'm not gonna because I have numbers already written down. So just be aware of that. We should be using A equals this and B equals negative 0.758. But I used my old book when I wrote this and I haven't fixed it, and they used for A 39.90, and we leave the ultimate strength in KSI, and raise to the negative 0.995.
Should the 54.9 be 12.7 for the
Oh, you're right. You're right. It should be.
I know we're not using any like this.
You're right. Sorry, I jumped at. I looked the wrong spot. And we have 12.7. Thank you. Something I want to double check here. I'm now not certain of something, so I want to take a look. I want to see if anybody joined us. No, no one's joined us. Okay. If we go to notes in here and we come down to class 20, you'll see that I have the 11th edition and the 10th edition, the factors. So here's the 10th edition, and there it is. There's the 39.9 and the 0.995. Okay, so just wanted to point that out, that they're available up there. If someone has the 10th edition and they want the 11th edition, or somebody has the 11th edition, I didn't specify, and some people might have already done the homework, so whatever book that you have, use that. Or if you're listening to this right now and say, I want to use the 11th edition, but I only have the 10th, just use the figures I provided. So anyway, this is a pretty low number, 0.4083. That's not typical of most of these factors. They're usually hovering somewhere close to 1. This forged has an effect, right? It's rough surface. And now we also need, okay, so we want to have the next KB, but the KB is all based on the diameter here. We need to have it, we don't have a diameter, and it's not rotating. So we go to table 6.3 here, and look down, oh, there you go. And we have an area right here, and what did I do with this? Trying to remember actually, interesting. The old version had an equivalent diameter here, but they did something with the area, trying to pick this off on the fly. What did you do here? We took 0.05 VA. Yeah, that's interesting. They have A is equal to that, but I had Anyway, I think I might have been using this wrong, or there's a difference in this, because I should not be using A. I should be using DE. You'll see there's a DE up on this one. There's an area for the thing, and there's a DE. And I'm trying to remember what to do about that. I think what I should have done was to find that area and then work backwards and figure out what diameter I would get in order to get that. I think that makes sense.
Are we still treating it like an I-beam if we're just looking at the top section?
It's a good question.
Like, if we're just looking at the top flange, can we just use the rectangle?
I think we're gonna go stick with this, because it is an I-beam. Okay. We only did that for the stress concentration. Okay. Because the stress concentration is based on local stuff. Right. And we're trying to, and I'm just saying, this is what I'm thinking of. I mean, honestly, we used the maximum that they had. So even if we used the entire width of the I-beam, we would still be using the maximum that they had. Right. Maybe no, R divided by that. I'll take that back. Okay. All right. But here this is applicable to the I-beam. I'm just concerned that I think what I should have done was to take this area that I get and find the equivalent diameter. I have to get back to that. I'm going to continue with what I have, but just be aware that I'm suspicious I'm wondering what I did before. So I said that I was going to use an equivalent diameter of 0.05 BA. But that's, and where B is the, they gave us the dimensions here. They said B is the height of the thing and A is the flange width. So looking back up there, the height of the thing, the depth is 8, and the flange width is 4.001. So I said 0.05 times, B, let's see, is 8, and flange width, I just said is 4, so I get 1.60. I think this should have been actually the area, and then we can find the diameter. So there's a source of error for you. So I come back to this. So I would actually find the equivalent diameter, and then plug that back into this. You'll notice that it's between 0.3 and 2, right? We had 1.6 is what I'm saying it's going to be. So we can use that 0.879 D raised to the -107.
So are you saying if we're using the A with the I-beam, you would find that A, and then plug that in to the A in the rectangle to find H and B, and then use the H and the B to find B in the function under there?
Okay, well, here's what I think I should probably have done. I should probably treat this like an area and say, well, I mean, I know that the area of a circular one is pi over 4d squared, right? So that should be 4 times the area divided by pi, take the square root, right? And I also just noticed, I'm distracted, that I think I might have used, boy, I'm really finding all certain cylinders. I think I used the wrong equation. But I'm just really, this is just a wonderful, what a wonderful job this was. So anyway, I would have instead, so that was 1.6 times 4 divided by pi and taken the square root, and I would have gotten, okay, that's not that bad, 1.427. I think that would be like the equivalent diameter, because they gave us an area. Right? I don't know why they gave us an area instead of an equivalent diameter. So I would say this is the equivalent diameter. And then I would have plugged it into this, but I used the wrong number. So I guess we're gonna have to fix this as I go along. So I'm gonna fix it as I go along in here. So I should have used, because this is in between 0.3 and 2, I should have used this equation, but I used this one in my calculations for some reason. I must have been in a hurry. So 0.879 raised to the -0.107. So we go, where are we at? 0.879, 1.427. We might as well use that one. I think it's correct. And a lot of times this is a lot of work for very little reward. Right? We're gonna do all of this, and it's going to come out to like 0.97, right? It's like, okay, great. Just think of all the error we already had, right? So this is 0.8462, right? And what did I get before? I got 0.845. I guess it wasn't too bad off in terms of the result. Okay, so I'm going to go to case C now, which is case C in the sunshine band, comes to my mind. And case C is going to be equal to 1. Why is that? Because this is in bending. And so the case C is the load factor, and it really accounts for things that are other than bending, right? So if it's bending, it equals 1. Makes sense. The next is going to be the KD is the temperature factor. And we said that it was 300 degrees Fahrenheit. Now, in other editions, they were nice enough to make a table, and they didn't do that in this edition. They do give us an equation though, and I don't know why they don't say KD is equal to this, but that's what they mean. Don't understand, don't know it. But I think that we will get pretty darn close if we stick in for the equation here of 0.898 plus 3.5 E minus 4 times our temperature, which I'll put 300 in there, minus 6.3 E to the minus 7, and 300 squared. So let's see how close we get. It's going to be pretty darn close. 0.98, 300 times 3.5 E4 minus times atom, and then 300 squared times 6.3 E7. Doesn't change it much. I get 1.142. And previously from the table, I got 1.024. That's actually, I feel as though I made a mistake in doing that. So let me double, triple check here. 300, 3.5 E4 minus times 0.98 added together. And then the 300 squared and 6.3 E7.
I got 1.028.
You got 1 point what?
028.
Really?
Yeah.
I just did it wrong twice? Because I got the same thing wrong. I got the same thing twice. I got the same thing and then, huh.
Let me double.
Yeah. This is going to make for an exciting video.
4 times 300 minus 6.3 times.
Oh, you know what I kept doing? I did the same. You were right. You're right. You're going to be right. I know what I did because I didn't subtract it.
Oh, gotcha.
Yeah. Oh, well, now I got a different number. What'd you say you got?
1.028.
Yeah, okay. Me too. Whee! Excited. KE is a reliability factor. What did I say? I wanted 90% reliability. We don't have to calculate anything on that. Yay for not calculating. Oh, but I can't find it. It's in the table. It escapes me. Where'd it go?
Good question for the temperature thing. Is that like, I don't know if we've ever, wait a second. No, I'm not. That's the TF is where, how it, like what temperature it's made at? Or,
Oh, no, it's the temperature at which it's operating at.
okay. So does that account for negative temperatures as well?
Not really.
Okay.
No, I don't know what you would do necessarily for that. That becomes kind of more fractional mechanics. You get some hazards for fractional mechanics involved in that. Outside the realm of this,
Right.
I think. Anyways, okay, so for the 90% reliability, we're going to take 0.897. So the KE is 0.897. So now we're going to get our endurance strength with the KA, KB, KC, KD. So 0.4083, which we totally could have fixed now after having done all that. 0.8462, 1.028, and 0.897. See, I was trying to create an example that was messed up. You know, that had everything in it, or a lot of stuff in it. So 0.4083, 0.8462, 1.028, and 0.897, and 50. And I got a very small 15.93. What did I get last time? I got 15.85. Okay, so we're in the same ballpark. That's good news. All right, so now that we got this endurance strength, after we modified it, we want to find the parameters to populate the equation that looks like this. Remembering that A and B are not what we found in that table. So we go to this figure, and for 100, we get like 0.84 and change. You see that 0.85 is right there. So 0.843 or something like that. What did I say before? I had 0.843. So I said F is approximately 0.843. We could also, they also have an equation for that now. Right? So we could also have used this equation if we wanted to, just to see what we would get. Notably, if we're below 70, we just use 0.9. Right? So that just to keep that in mind. And it's often convenient just to take that ultimate strength and multiply it by that F. And that was 100, we could do that in our heads, 84.3 KSI. Right? Because when we go to our A equation, that's FSUT squared divided by SE, which now we're going to 84.3 squared divided by our 15.93. I'm going to change a little lot, I guess, but 84.3. Oh boy, that's okay. 446.1, and then B is equal to negative 1/3 log of FSUT over SE. And so 84.3 divided by our 15.93. So 84.3, 15.93 divided, take the log, divide by 3, and that ends up being negative 0.2412. Not too much different from what I had before. And so N is going to be equal to, I'm putting it into this. We have this, with the stress concentration, remember we got a 72.01. This is being divided by 446.1 and raised to the 0.2412. So, shoot, put that over, 72.01 and raised to, well,
should that be negative or 1 over?
Yes. Thank you. So I'm going to do it again. I had it in my calculator. It was going to be so great. And then 0.2412. That makes a lot more sense. 1,922 cycles. So we want to say 1,900 cycles is what we're predicting for the life, because we don't want to imply we know when it's going to fail. All right, so estimate the life of the thing. And they don't tell us the frequency of this load, otherwise we can come up with time, which is maybe a better way to try to convey that. I think No, this isn't right. I could probably use the scale though. Yeah, I'm gonna cheat and I already have this printed out right here, but this is, so I could double dip and didn't bring my awesome thing, but anyway, ultimate strength is right here at 100, right? And the F times the ultimate strength is 84 point something, right? We said it's 100, 84.3. So here's 8 and there's 9. So we come over to 1,000 right here. And so that's somewhere like right in there. Right? I guess I'll use this. Let's see if the paper. This is not going to be great. This is not going to work over. Not a great drafting tool. It's in there to the paper. And then we also found that the endurance strength was 15.93. So looking at this right here, we don't want to go halfway. It's actually up higher, right? So it's like somewhere like right in there. So we want to get over to here. Do you want to roll? I can almost make it up to the thing. No, here we go. I'll fix this. I have to get up off my chair, and that would just be too much, right? It would be too much to ask.
Just throw it at you.
Just throw it. Just throw it. All right. There you go. Hand down. And our stress was, what did we say our stress was? 72. So up here somewhere, so it's gonna be like right in there. So like right in there. So we can see, okay, here's 1,000 here and here's 2,000. Pretty good. Pretty good. All right. So there's another example with a lot more complicated. And one of the things I meant to do this afternoon was to record this example. So now it's recorded. Yee. Mixing. I've never seen it do the mixing the audio. I wonder if it recorded the audio. I don't know what microphone it used. It might use that microphone, which is really my favorite. That thing has a microphone. I think. Should have tested it out. Don't know. But should have covered. Anybody join us? No. Is it uploading? What's it doing? There he goes. Uploading. Okay. Ooh, it's uploading fast. That's not good. So what microphone is it using? It does say indicate a microphone. It says the default one. I don't know. Okay, we can continue. Okay, so what kind of other problems would you like to see? We're still recording onto this guy too, right here, right? Yeah, we're recording. So what other kind of problems would you like to see? You don't have to, by the way. This is a personal attention that you're getting.
Great. I'll be honest, I haven't looked at the home yet, so.
That's fine, but this should like kind of set you up with quite a bit of it, I think. But one last thing I have to do. I have to grade. Oh, great. I'll probably procrastinate. Chance stuff. I'm quite the procrastinator. Anything on the exam or like I mean this is being recorded, so I don't say anything.
Well.
All right. Well, let's call it. I don't know. We don't have to do anything.
Right.
It's all about like trying to help, be helpful, and
Cool with that.
if you're feeling comfortable with it, I'm feeling comfortable with it. I'm not going to force you to be the representative of all those who didn't show up and hurt my will feelings. Thank you for your pencil. You might want to sanitize this so we don't give COVID to each other. Don't touch it for very long. Maybe that keeps the germs off. I don't know if that's how that works.
Let them die of starvation.
One of the guys in my band, the other guitarist, he works for Pfizer, and his main project, the main thing he's been doing is the pill they just announced today. The COVID pill.
Huh.
If you get exposed to COVID, it's got something like 80+% effectiveness of not getting into the hospital.
That's pretty good.
And it's been so effective that they decided to end the testing of it early and go to and then go to the FDA and say we want to get it cleared now. That's how effective it's been. They just announced it today, so.